Welcome on the next video on stochastic calculus. In this video, we will continue talking about the Brownian motion and its filtration. Let me start sharing slides. So this is the second part on the Brownian motion. In particular, we want to discuss properties of the natural filtration generated by the Brownian motion, or the Brownian motion. Okay. So for this, let us recall where we stopped in the last video, which was the natural filtration generated by a stochastic process. Okay. So as you hopefully remember, every stochastic process let's call it X. And as before, we have a stochastic process, meaning a sequence of random variables, which is indexed by a time interval 0 to t. And then its natural filtration is defined as fx. So this is the x refers to the stochastic process, and then it's the minimal filtration you need to consider in order to make the process x adapted. This means, so I consider the sigma algebra generated by the pre-images of all these random variables xs, where s is less or equal than t. Okay, so that's my natural filtration. Okay, so this is the definition of natural filtration. So what is this is certainly the natural choice for a stochastic process to consider an associated filtration. But the issue is fxt often has, not the desired regularity regularity condition. So as we will see in the next example, natural stopping times might be not stopping times if we just consider the natural filtration. And this is why in the next step, then we want to consider some regularized version of its filtration, of the natural filtration. And this even in case of a Brownian motion. So let's come to the example 2.3. Where we consider a stochastic process and then consider the natural filtration as well. So how do we define our stochastic process? So what we do is to keep we want to have a simple toy example. So we consider the set A, which is part of our sigma algebra, and we don't want to take neither the empty set nor the full sample space. Okay. And in this example, what we do is we consider xt defined as follows. So xt is, okay, two cases. The first case is, okay, I am in the set A. So this means I consider t minus 1 multiplied with the indicator function that t is strictly bigger than 1. And this is if t is in 0 and 2, right? So, okay, can take a general t, but let's choose t equal to 2 to make it a bit more concrete. So that's right. Okay, this is if omega is in A. And of course, T here is in 0, 2, as I wrote. Right, so this means the process is constantly equal to 0. And if we at time 1, if your omega is in A, we start increasing from 0 to 1. And if we are in the complement of A, well, we start decreasing from 0 to -1 if T is strictly bigger than 1. Right? So okay, let's draw a picture how this process looks like. Yeah, so this is right. So here we have somewhere 1, here we have 2, and here we have 1 and -1. Okay. All right, so my process then looks like, okay, I'm staying, the process is equal to 0 up to time 1. And then at time 1 is either going up or it's going down, depending whether my scenario here, omega is in the set A or not. So this is green here is process xt. Okay. Okay. So what we see here, well, x is a continuous process, right? This is, if you look at the sample part of this process x, it's a continuous process. Well, it's random, so it's a stochastic process. And this means it generates a natural filtration. And if we start considering the natural filtration here, well, what is it? Well, if we are, again, we have two cases, right? Up to time 1 and after time 1. So if T is between 1 and 0, 0 and 1, well, what is this? The minimum filtration I need to make this stochastic process measurable is nothing else than the trivial one. Right? Because this are just constants. So the process is constantly equal to 0 up to time 1. So in order to make it measurable, I need the trivial filtration. And after time 1, so in the interval, the half open interval from 1 to 2, what do I need? Well, after time 1, I can decide whether I am on the set A or on its complement. So this needs to be added to our filtration. The sigma algebra for generated by the stochastic process for times strictly bigger than 1. Complement. So the filtration here, the natural one also generated by x, is rather simple. Okay. This is a rather regular process. The process is continuous. But what we have now is, if we look at the time tau, which is the first time in our interval 0 to t, to 2, that xt is the stochastic process is strictly less than 1. Then we take the minimum to 1 to have a finite one, is not a stopping time. Why? How can we see this? Well, okay, stopping time, let me be precise. Of course, I mean here with respect to the natural filtration generated by the process xt. How do we see this? Well, that's actually not so hard to see. Well, what we need for stopping time, if you hopefully you remember, I need that the event that tau is less or equal than 1 is F1 measurable. Okay? Tau is less or equal than 1 exactly if tau is equal to 1. Right? Because before that, I am constantly equal to 0, so I'm not strictly less than 0. The first time where this can happen is equal to 1 at the time 1. But this here, the event that tau is exactly equal to 1 means I'm going down here. So I'm becoming negative directly after 1. So this happens on the event a complement. But a complement is, if I look at my natural filtration, is not included in the filtration generated of the process X at time 1. So this is not a stopping time. And this is something undesirable because we want that hitting times of sets like this is an open set to be a stopping time. So but we want that hitting times because it makes our life much easier, like tau are stopping times. Okay, so what does it mean for us? Well, this means we need somehow to modify the filtration in order to restore some regularity property of it, and in particular to ensure that hitting times of open sets are stopping times as well. So what do we want? So want to, let's call it, regularize the natural filtration of stressing processes. Or general, want to regularize natural filtrations. Okay, so how can we do that? I mean, this is a standard thing we want to do. Okay, the first thing what you might have seen in some probability calls already is you want to include the null sets. Right, and this is why we want to have a completed probability space. So let me recall here how do I label the null sets. So set so these are all F, right? All events in the underlying sigma algebra F, which have the probability measure there. And recall, I mean, we always work on a completed probability space. So here, basically, all the null sets floating around are included in the sigma algebra. So this is what we call P null sets. Set of P null sets. Okay. So the second thing, which we want to make sure that our natural filtration is that it's right continuous, which is here not the case. If you look at the counter, the example here, you see this filtration somehow has suddenly increasing. Okay, so and these two conditions, I would like to ensure that my filtration always fulfills them, are included in what's called the usual condition. So let me make the following definition. The filtration Let's call it F. It's a general filtration, but of course this definition also works for natural ones. Set to satisfy the usual conditions. If, okay, and this is what we define with usual conditions. First assumption, as I said, I want that the sigma algebra at every time contains the null sets. This means we just want to ensure that this contains all p null sets. Okay. Because this is an increasing sequence, so if F0 contains all p null sets, then all the other sigma algebras at higher times will also include the null sets. This is what's called completeness. Okay. And the second thing I would like to ensure is the right continuity, which is some regularity of the filtration. And I want that the filtration at time t is equal to the filtration at time t plus. So what is as t plus? This means I want to come from the right side, meaning I take the intersection of all filtrations Fs, which are strictly bigger than t. So would I have here an equality sign as well, then, okay, that would be trivial because I have an increasing sequence of filtrations. But here, it is important, I have the strict inequality here. And then it's not trivial, right? If you look at the example, as I said, this will not fulfill this at time 1. And I want to have this holds true for all t. I exclude here the terminal time because they have no right sign. So this is what's called right continuity. Okay. So as you have or will see on the problem sheets, I mean, the right continuity is rather useful in order to, for example, ensure that such hitting times are indeed stopping times in general. Okay. And now the question is, coming back to the Brownian motion, which is the most central object or stochastic process we will deal with, what does it mean for also how do I ensure that the filtration generated by a Brownian motion indeed satisfy the usual conditions? And that's the next thing we want to understand. In the case of a Brownian motion, it's actually enough to assume that the null sets are included in F0. If we do this, then the Brownian filtration, so the filtration generated by a Brownian motion, immediately fulfilled the right continuity assumption. Of course, this is in general not true. So for a general stochastic process, completeness and right continuity are really some different assumptions, and you need to make both in order to have a nice life with the filtration. Proposition 5. Okay, so let's come back to Brownian motion, which is the main stochastic process we want to deal with. So I consider Brownian motion, right? And then I consider the completed natural filtration. Natural filtration. And I want to call it, for simplicity, just F. The reason is because in the future, we will always work with this filtration. 15. How is it defined? Very simple. You take the natural filtration of the Brownian motion, so the one generated by one at time t, and then you add the null sets. And this is your new completed natural filtration. Okay, this is okay. And what I am claiming in this proposition is that this is already right continuous. Meaning ft equals ft plus. And well, since the definition U, let me recall the definition. It's the same. So I take the intersection of all filtrations strictly bigger than t. All right. So for Brownian motion, but this is special. Special situation with the Brownian motion, completing the filtration already means we get a right continuous filtration. Let's come to the proof. The proof is a bit technical and might assume some results or use some results you haven't seen, but I will do it for completeness reason anyway. But I mean, don't be. I mean, if you haven't seen, it's not. So if I will claim or explain which results I use, if you haven't seen them, you can find them in the appendix as well. But I will not prove then. I mean, the additional results I need to use. Okay. Okay. One direction is obviously easy, right? So if I have my filtration at time t, it's certainly included in the filtration ft plus. Because my filtrations are increasing, and this includes all. I mean, this includes all s. Strictly being bigger than t is yes. Okay, so this is the easy one. So what we want to show the other direction. This means I want to show that ft plus is also included in ft, which is not clear because, well, we have here always bigger filtration. Okay. So what does it mean? We want to show the following. If I have a set A in my filtration ft plus, it means it's also a set in ft. So this is what this statement here is saying. Okay. This is not so simple. So the first thing I want to show is if I take a function f, which might be mapping from Rd to R, which is assumed to be continuous and bounded function. And D is, I take my points T1, T2, up to TD, right? They're all included in our interval 0 to T. We have that the conditional expectation of f evaluated the points bt1 up to btd condition on the filtration ft plus is ft measurable. Okay. So this is the claim I want to show here. And this is to be consistent with the lecture note. This is 2.1. Okay, what's the issue here, right? Just to recall it, I mean, this here is in general, if you look at this conditional expectation, this is in general only ft measurable. So it's not clear ft plus measurable, right? This is because you restrict, I mean, you take the conditional expectation with respect to ft plus. This means the conditional expectation, you know, the random variable you get out is only, I mean, in general, only ft plus measurable. And we want to have a stronger statement that it's ft measurable. Okay, so let's do this. And this is the first step we want to do. So, how do we prove this? Okay, without loss of generality, we might assume that there is a constant k, so which is between 1 and d minus 1, such that f the t is somewhere in between tk and tk plus 1. Okay. And furthermore, choose, right, if there's no such k, I mean, okay, this is the function f evaluated at the Brownian motion. The points of the Brownian motion is anyway ft plus measurable, so we can pull it out, and the statement is trivial. So this is what we assume, that there's somewhere t which is in the one of these between one of these t1 up to td points. And next, okay, we want to choose n real number large enough such that it's between, so it's large enough that if I add this 1 over n to t, it's still less than t at tk plus 1, right? So, okay, so this is the two things I want to do. And now I want to analyze this conditional expectation, for which I want to show that it's ft measurable. Okay. Let's start analyzing this. And now here, okay, this is a trick we will see at several places. What do you want to? Okay, you know that the increments of the Brownian motions are independent. Oh, yeah. Okay. Okay. Okay, we will show this later. So we know that this is independent. So let's. Okay. Right. Okay. Sorry. This is the same line I wanted. Right. So what you do is the standard trick is, well, you add and subtract in order to get increments. Right? This means, so I look at I add here the Brownian motion at time t plus 1 over n, and then I need to subtract it as well. Okay, and what? I need to do this up to my terminal time. So I make the same trick from tk up to td. Okay. And now I can factorize this out. So I can integrate over the last d minus k components. So what do I get here is f evaluated at time ft y, Brownian motion up to the Brownian motion at time tk. And now I can replace these increments by constant k over which I want to integrate. Okay. Where, oh, I forgot my density function, right? So if I integrate, I know that these are random. So I forgot it has to be multiplied with, of course, the density function. For Brownian motion, this is just a normal distribution. So these Pn are just my normal distribution of these independent increments. Oh, they're not independent, sorry, of these increments. Where, okay, I need to see what Pn is. So Pn is, denotes the probability density of these increments here. And this is just a normal distribution, so there's nothing to worry about. Okay, it looks a bit lengthy. No. Okay. Okay. So now we observe two things. Observation 1. Tau n goes to Pn goes as well to p pointwise. As n goes to infinity, and p where p is just the probability density of the vector tk plus 1 minus tt td minus tt. Okay. Okay, so that's good. So this is the first observation, and this means what we get is that this here, so let me go from here down there, goes to, if I send n to infinity, this is nothing else than K. Right, so I use dominated convergence. Why dominated convergence? The dominated convergence theory. This goes to K T minus K1, right? And then they're multiplied with the probability density of P, which is D K minus 1. Okay, so the good thing is that I know that this here is FT measurable. Okay. This is FT measurable, and this means this is nothing else than if I take here the limit. So the limiting object, if I send n to infinity of the conditional expectation condition on FT plus 1 over n is FT measurable. The question is, what is it? And this brings us to our second observation. The second observation, if I look at this conditional expectation here, TD, conditioned on FT plus 1, and I consider it as a discrete time process, is what's called the backward martingale. So if you haven't seen a backward martingale, don't worry. I mean, this is the only place I think where we use it. The point is that if you look at this as a process, it's a martingale with a shrinking filtration. So if you look at the definition of a martingale, there's nothing special to the filtration, right? You could take any. The filtration here is somewhat shrinking. That's all what it is. So this is why it's called backward. And the main point is this means this, if I look at the limit n to infinity of this object, I can show, I mean, this is for example part of the Wahrscheinlichkeit C2.1 course, I can show that this goes to exactly the object I wanted to have. Namely, the conditional expectation of this f applied to the Brownian motion at ft plus. Okay, the limit is taken in one, I think, or P almost surely. So this is the convergence theorem for backward martingales. I mean, it's rather useful, but it's actually not so hard to prove. And if you want to check it out, for example, see the appendix in the lecture notes. Okay. And now we need that the null sets are included in our filtration, because we have now that this here converges to the right object, and this here to something FT measurable. But I mean, these are both almost sure limits. So we might have different null sets. So we need to be careful that we keep the identity here. And this is where the null sets come in. So, right, so this means that my claim holds. Okay. So this is my claim, just to recall it for you. Means if I look at this conditional expectation with respect to ft, it's even ft measurable. Okay. And now I can say use dominator conversion theorem to say, well, 2.1 holds for all indicator functions are right, with the set A for all A in the filtration generated by BT1 up to BTD. Okay. And now what the standard extension arguments, so Duncan's system, or if you look at Duncan's argument, what tells you, well, you can conclude that if you look at indicator functions in general and restrict them to ft plus, this is ft measurable for all A in ftd. And this means also for all A in ft. Right, you can, at the null set, we will see the argument in the next lemma as well. I mean, spelled it out there. You can add the null sets. Okay, and this means, I mean, we're almost done. So for all A in ft plus, we have that A is equal to the conditional expectation, right? This is, if it's measurable, if A of ft plus measurable, we can also pull it out, the conditional expectation. But we have shown that this conditional expectation is still ft measurable. So what we saw, if we have an indicator function often set in ft plus, it's also ft measurable. And this means A is in ft as well. And this holds for all ft plus measurable. So this is actually what we wanted to show, that every ft plus measurable function is also ft. Yeah. Right, so this is the original claim. Okay. Okay, so implicitly we have already used the fact, which I actually haven't shown. So, I mean, the order of the lemmas is suboptimal. But, I mean, we need to ensure that the Markov property, which we already used, is still in place. And this is what we, I mean, briefly do or check in the next lemma. Okay. So let's, as before, I mean, I have a Brownian motion. Brownian motion. And I consider ft completed filtration. Okay. And then for st, part of my interval 0 to t, what do I have? The increment from B to S is independent of the sigma algebra at time S. Okay. Proof. So, I mean, this is, I mean, we already used it, but so just let me quickly convince you that this is true. So what do we want? So to show or to prove that b minus b at time t minus b at time s is independent of ft, we need to show. And so what I do is I want that if I look at the set generated by this increments of a Brownian motion, so I look at the indicator function of b of the set E, and E is just a Borel measurable set. And then plug in the increment. Then I multiply it with the set F, which is in the sigma algebra of S. Well, this, I mean, by the definition of independent, this should factorize. So this means this should be the expected value of E, the indicator function of E applied to the increment here should be the same multiplied with the indicator function. Okay. Right. So, okay. Now, what do we know? Note for all f in S, there exists a set f prime in the natural filtration generated by the Brownian motion, such that if I look at the symmetric difference, so if I cut away this set f prime, this is a null set. Right? So this means, well, if I have an object in the sigma algebra fs, they are always given basically by a set in the sigma algebra generated by a Brownian motion at time s, and then added somehow null set. This is what we do if we complete it. Right? And so how do you see the claim here, where we just need to cut away the null sets? So we start here at the left-hand side of our claim. Well, since we work under the expected value where we can throw away null sets, this doesn't matter. So I can replace the indicator function of f by the indication of f prime. Here I know by that this, I mean here I know that the increment is independent of f. The natural filtration, right? This is the fact I gave you in the last video. So I can factorize this out. And then I can add the null sets again. So let me write it below here. And this is, so I can replace the indicator function of f prime by f again. And this is the claim I wanted to have. Right, so that's all. Okay, so I mean, adding the null sets to the natural filtration of the Brownian motion, I mean, so completing it doesn't destroy the Markov property, and this is also okay what we implicitly already used in the last theorem. Okay, so let me conclude this video with two remarks. Well, which is one, two, 7. Okay, first thing is, okay, just some terminology again. So F, or filtration F, so the completed one of the Brownian motion here is often called Brownian standard filtration. Yeah. It's not the natural one, but it's the one usually used. So this is why it's called standard filtration of a Brownian motion. And second thing, which I mean, you might say, okay, I mean, what did we do? As we said, okay, one property we wanted to have is we wanted to get a right continuous filtration. So an alternative procedure, which appears also in many books, is the following. So in order to obtain a Brownian right continuous filtration, what I could do is just take the natural one. So to make the Brownian filtration right continuous, we could set, well, what we do is, well, we just introduce F plus T, well, which is hard coded to be right continuous, right? So you take just the natural one and take the intersection of all natural filtration at time S being strictly bigger than T. So this is by definition a right continuous filtration. Okay, we could do this. So this is T plus is right continuous. Oh, why can I not? And ft minus the increments are independent of ft plus s, right? But this is harder to show, right? This is so I mean, we're not doing this. We will always take the Brownian standard filtration, so we're just adding the null set, and then we get the filtration with true. But just note that, I mean, the difference to this approach is actually, I mean, they're only the null set. So the difference of FTD and F plus are essentially in the p-null sets. Right? This is why adding the p-null sets makes it already right continuous. And where you might have observed it is, if you have seen it, otherwise it's, I mean, just a side remark. If you look at Blumenthal's 0-1 law. which tells you basically the events which are in the right in F plus, but not in FB, either 0 or 1 sets. Okay. So what I mean, we will always take the Brownian standard filtration, the following. Just this other one, the detour to the alternative approach is just a side remark, as you might see it in some books. So we take the standard filtration, meaning we take the natural one, add the null sets, and then we have a right continuous filtration with which we want to work. All right. This is all I wanted to say in this chapter regarding the Brownian motion.